Hello, I welcome you all in today's lecture. Here in this lecture, we'll work out a design example on bearing type bolted joints. So as you can see in the slide, we have to design a bolt joint to connect two tension members of section 240 mm by 12 mm and 240 mm by 20 mm. And the members carry effective tensile load of 250 kN, and we have to design the bolted joint for three different cases which will be followed. And we have to use the bolts of grade 4.6, and the grade of the steel for the tension members is E250, which is actually as per the new grade designation system as proposed by IS 2062-2011. And the three different cases for which we have to design the bolted joint are: case 1, if the members are connected by lap joint; case 2, if the members are connected by single cover part joint and the cover plate being 10 mm thick; and the case 3 is if the members are connected by double cover part joint and each of the cover plates being 8 mm thick. So let us begin. Now, referring to table 2 of IS 2062-2011 for E250 grade of steel, the ultimate tensile strength, that is Fu, is given by 410 Newton per millimeter square. That's from table 2 IS 2062-2011. And for the bolts of grade 4.6, the ultimate tensile strength, that is FUB, is given by 400 Newton per millimeter square. In the grade designation system of bolts, the first number in the grade designation actually denotes 1/10 of the minimum ultimate tensile strength of the bolt in kgs per millimeter square. So we have to multiply the first number by 10 in order to get the ultimate tensile strength of the bolt. So we will multiply it by 10, that is 40 kg per millimeter square. And when we convert into newtons per millimeter square, we will get approximately 400 Newton per millimeter square as the ultimate tensile strength of the bolt for the grade 4.6. Now, as we have to design the joint for three different cases, let's take case 1, that is the case of lap joint. Now, in the case of lap joint, the bolts will be subjected to single shear. So let us take two plates which are being connected by a lap joint. Let us say we have a bolt line here. So the bolt in the case of lap joint will be subjected to single shear, that is there will be only one plane of shear, and that is at the interface between the two plates. So we call it single shear case. So the bolts are subject to single shear in the case of lap joint. Now let's assume the shear plane lies within the threads of the bolt or within the thread portion of the bolt, because we have the plain shank length in the bolt and we have a threaded portion in the bolt. And if we assume that the shear plane lies within the threaded portion, we will be actually on a safer side of the design, because in the case when we assume the shear plane being within the threaded portion, the net cross-sectional area of the bolt at the location of the threads will be smaller. So actually we will have a smaller value of shear capacity of the bolt. So Consequently, we will be on safer side of the design. That is, if this is the bolt and we are assuming that this shear plane lies within the threads, so we will have actually threads like this up to a level which is above the shear plane level. Now the design. Shear strength of the bolt, that is VDSB, is equal to VNSB, that is nominal shear capacity of the bolt, over gamma MB, that is the partial safe factor of safety for the material of the bolt. And we have VNSB equal to, that is nominal shear capacity of the bolt, that is FUB over under root 3 NNANB plus NSASB. So we will have the design shear strength for the bolt equal to FUB over under root 3 multiplied by gamma MB NNANB plus NSASB, where NN is the number of shear planes that intercept the thread portion, or the number of shear planes that lie within the thread portion. And in this case we have NN equal to 1 because we have assumed that the shear plane lies within the thread portion, and ANB is the net cross-sectional area of the bolt, that is at the location of the threads, or the net stress area of the bolt, and NS is the number of shear planes that lie outside the threaded portion, and ASB is the cross-sectional area of the shank of the bolt. So let's assume 20 millimeter diameter bolts. You may assume the diameter of the bolt is at your own will. So let us take 20 mm diameter bolts. Therefore, A and B is net cross-sectional area of the bolt at the location of threads is 0.78. It is taken as 78% of the cross-sectional area at the level of the shank portion. So it will be 0.78 pi by 4 d square, where d is the nominal diameter of the bolt. So you will get 0.78 pi by 4 into 20 square, that is 245 millimeter square. So this is actually the cross-sectional area of the bolt at the location of the threads. Now we have NN, there is number of shear planes intercepting the threaded portion, that is 1, because we have only one shear plane and that's intercepted. We have assumed that it intercepts the threaded portion. And NS is 0 because there is only one shear plane, and we have assumed that the shear plane is intercepted by the threads. So the number of shear planes that are outside the threaded portion is 0 because there is no shear plane outside the threaded portion because we have only one shear plane. And gamma MB is equal to 1.25, that is safety factor, rather partial safety factor for the material of the bolt, that is from table 5 IS 800 2007. So we will have VDSB equal to FUB, that is 400 divided by under root of 3 multiplied by 1.25. NN is 1 multiplied by ANB is 245 plus NS is 0, so the whole term will vanish. We will get VDSB equal to 45,264.26 Newton, which will be equal to 45.264 kilonewton. So the design shear strength of the bolt is 45.264 kilonewton. Therefore, the number of bolts required from shear consideration is equal to total load on the joint over the shear capacity of one bolt, that is 45.264, that is equal to approximately 5.5, and we will take 6 number of bolts. Now step second, this was actually the design shear strength of the bolt, actually it was step first. Now the step second is bearing strength or design bearing strength. It is design of the bolts on the basis of bearing strength. So VDPB is equal to, that is design bearing strength of the bolt is given by 2.5 into KB into D into T multiplied by FU over gamma MB. Let us assume the pitch P equal to 2.5D, because this is the minimum value of pitch which we have to provide. We can even provide the pitch larger than this value, so let us keep the minimum value, that is 2.5D, as per this value is actually as per IS 800 2007. So 2.5 multiplied by D is diameter of the bolt, and we assumed the diameter of the bolt to be 20 mm, so you will get 50 mm as the pitch for the bolts. And the end distance and as well as the edge distance, we take it as 1.5 DH for machine flame cut or for sheared edges or sawn and planed edges, where DH is the size of the bolt hole. And we have E equal to 1.7 DH for hand flame cut edges. So DH will be equal to, that is size of the bolt hole. It is generally given by diameter of the bolt or diameter of the fastener plus clearance, and the nominal diameter of the fastener of the bolt is 20 mm, and the clearance is 2 mm for the diameter of the bolt when it is 20 mm, and you can determine this clearance value from table 19 IS 800 2007. So DH is diameter of the or size of the bolt hole is 22 mm. So that is E, end distance will be equal to 1.7 DH. Let us take the case of hand flame cut edges, or you may even assume the case of machine flame cut edges. So let's take E is equal to 1.7 DH, that will be equal to 1.7 multiplied by DH is 22, so you will get 37.4 mm. Let us take a value of 40 mm. This is the minimum value that you have to take. You can even take a value more than this. Therefore, we will determine the value of KB. That is, KB is E divided by 3DH and P divided by 3DH minus 0.25. We have FU divided by FUB over FU and 1. So we have to take the value of Kp from these values and we have to take the least among the values. That is, value of Kb will be equal to 40 divided by, because E we have taken as 40, 3 multiplied by 22, it is 50 by 322 minus, actually 0.25. FUB we have 400 by 410 and we have 1. So we have 0.60, 0.51, 0.97 and 1. And we have to take the least value from these values. Therefore, the value of Kb will be equal to 0.51, which is least among the values. Now, the design bearing strength of the bolt VDPB will be equal to 2.5 multiplied by KB, that is 0.51, multiplied by D, that is 20, multiplied by T, and we have actually two plates of 12 mm thickness and 20 mm thickness, and we have to take the least value, that is, we will take 12 mm. So 12 multiplied by 410 over 1.25. So you will get the value as VDPB 100368. That will be equal to 100.37. It is actually Newton. So you will get 100.37 kilonewton as the bearing capacity of the bolt. Now the strength of the bolt will be minimum of the strength in shear and the strength in bearing. So in other words, we may say the bolt value, that is the minimum of the strength from shear considerations and from bearing considerations. That is, we have bolt value as minimum of shear strength and bearing strength. So this will be actually minimum of 45, that is the shear strength 45.26, and the bearing strength, that is 100.37 kilonewton. So we have to take the minimum of these values. So the bolt value will be equal to 45.26 kilonewton. Hence, the strength in the case of lap joint is actually, in this case, governed by shear, because the shear strength value is less than the bearing strength value. And the number of bolts required from shear strength consideration, which we have already calculated, is number of bolts required will be equal to 250, it is the load on the joint, divided by the capacity of the joint, and this capacity is actually governed by shear, so it is actually shear capacity. So 45.26, that is equal to 5.5, and let us take 6 number of bolts. So let us show the arrangement of the bolts. In the case of lap joint, for the case first, so we have 6 number of bolts required. So let us arrange the bolts in this fashion. And this is the pitch which we have assumed as or determined as 50 mm, that is 2.5 times the nominal diameter of the bolt. We have taken it as 50 mm, and the end distance we have taken it as 40 mm. We have also assumed that the edge distance and end distance are same, so we will have edge distance as 40 mm, or you can take different value for the edge distance, but let's assume that the edge and end distance are the same. So we have 40 mm this, and 40 plus 40 will be 80. So the total width of the member is 240 mm. So you will get this distance as 160 mm. So this is the detailing for the lap joint, and this is actually the plan of the joint. And if you show the longitudinal section of the joint, you will have the one border line here, another border line, and another border line. So this is the arrangement of the bolts for the lap joint in the design example which we are actually taking into consideration. Now for case second, that is when the members are connected by single cover part joint. So in this case as well, the bolts will be in single shear, just as in the case of lap joint, and the thickness to be considered for bearing will be the least of the aggregate thickness of cover plates. And in this case, that's case B, we have only one cover plate, and the minimum thickness of the main plates jointed. Therefore, we will have T equal to 10, because if you take the aggregate thickness of the cover plates, that is, we have only one cover plate, that is 10 mm, and we have to take the minimum thickness of the main plates, that is 12 mm, and we will take the least from these two, that is T will be equal to 10 mm. Now the strength of the bolt in single shear, that will be equal to 45.26 kilonewton. as was determined in case 1, because in this case as well we have the bolts in single shear. Now the strength of the bolt in bearing is VDPB, and that's equal to 2.5 kb into D into T into Fu divided by gamma MB. So we have 2.5 multiplied by kb is 0.51 multiplied by 20 multiplied by 10 multiplied by 410, and gamma MB is 1.25. The value of kb will be same as in the previous case if we assume the pitch and edge distances and end distance to be the same, because the value of kb actually depends on the pitch and the end distances. So we have taken the same value of edge distances and end distances as well as the pitch, so we will get VDPB equal to 83640 Newton, that will be 83.64 kilonewton, and gamma MB value is 1.25, which we have already taken from the table 5. So the strength of the bolt will be minimum of the strength in shear and bearing, so therefore bolt value will be equal to the minimum of the bearing strength and the shear strength. So we will have bolt value as 45.26 kilonewton. And if we determine the number of bolts, we will get the same number of bolts as was calculated in the first case, because we have the bolt value 44.26, and in the previous case we had also the bolt value as 45.26. That is, in this case as well, the design is governed by shear as was in the previous case. Now we have case 3rd, that is when the bolts are in double shear. The thickness to be considered for bearing will be the least of the aggregate thickness of the cover plates and minimum thickness of the main plates. So the cover plates in this case 3rd is 8 mm. So aggregate thickness will be 16 mm, that is 8 plus 8, that will be 16 mm, and the minimum thickness of the main plates is 12 mm, because we have 12 mm and 20 mm. So we have 12 and 20 mm, and we have take the least from these, so you will get T equal to 12 mm. Now assume the shear plane, rather shear planes, because we will have 2 shear planes in this case, because the bolts are in double shear. Assume the shear planes lie within the threads, because in this case we have 2 plates and they are to be connected by cover plates. So actually we will have to provide a packing plate as well. So in this case the bolts will be subject to double shear, because we have 2 shear planes, one at this location and one at this location. That is, the 2 shear planes are at the interface here and at the interface here. So the number of shear planes will be 2, and we say that the bolts in the case of butt joint or double cover butt joint are in double shear. Now the strength of the bolt in double shear is given by VDSB, that is equal to FUB over under root 3 gamma MB NNENB plus NSASB, and we have in this case NN, there is number of shear planes intercepting the threads, that is 2, because we assumed that the shear planes lie within the threaded portion. So NS, that is number of shear planes outside the threaded portion, that is the number of shear planes which are not intercepted by the threaded portion, that will be 0, because we have only 2 shear planes and that are intercepted by the threaded portion. And the thickness of the plates, rather thickness of the packing plate, because we have the two members of thickness 20 mm and 12 mm, so there is the need of packing plate to be provided. So the thickness of the packing plate is 20 mm, the thickness of the thicker plate minus the thickness of the thinner plate, that is 12 mm, that will be equal to 8 mm. And this 8 mm is actually more than 6 mm as is proposed by the code. That is, if the thickness of the packing plate is more than 6 mm, we have to apply a reduction factor. That is, we have to apply a reduction factor beta pk, and that beta pk, that is reduction factor for packing material, that is given by 1 minus 0.0125 tpk, that is where tpk is the thickness of the packing plate. So beta pk will be equal to 1 minus 0.0125 multiplied by tpk, that is 8 mm. So you will get beta pk equal to, that is reduction factor which is to be applied for the packing material or packing plate, is 0.9. So the design shear strength of the bolt will be equal to FUB, that is 400 divided by under root 3 multiplied by 1.25, that is partial safety factor for the material of the bolt, and we have NN, that is number of shear planes, it's 2 intercepting the threaded portion, multiplied by ANB, that is 245, which has already been calculated, plus NS will be 0, so the whole term will be 0. So you will get VDSB equal to 81475 Newton, that will be equal to 81.47 kilonewton. So the design shear strength of the bolt will be 81.47 kilonewton. Now strength of the bolt in bearing, that is bearing strength of the bolt will be equal to VDPB, that is 2.5 kb multiplied by D multiplied by T multiplied by FU over gamma MB. So that will be equal to 2.5. Let us assume that the end distances and the pitch are the same, so we will get the same value of kb, that is 0.51 as is obtained in the previous case, multiplied by D, which is 20, this is nominal diameter of the bolt, multiplied by T, which is 12, that is least of the aggregate thickness of the cover plates and minimum of the main plates, and multiplied by gamma, rather FU, that is 410 over 1.25, which is actually the partial safety factor of safety for material of the bolt. So you will get VDPP, that is design bearing strength of the bolt, will be equal to 100,368, that will Newton, that will be equal to 100.368 kilonewton. Now the strength of the bolt will be the minimum of the strength in shear and bearing, that is the bolt value is minimum of the shear strength as well as the bearing strength of the bolt. So we have to take actually the minimum of the two strengths, that is shearing strength and bearing strength. So clearly we have bearing strength as 100.368 kN and shear strength as 81.47. So the design will be governed by shear in this case as well. So we have bolt value 81.47 kilonewton. And the number of bolts required for connecting the two members by the way of butt joint, or rather double cover butt joint, we will need the number of bolts as, that is number of bolts required will be equal to 250 kilonewton divided by the shear capacity of the bolt, or the bolt value, that is 81.47, that is equal to approximately 3. So you will need 3 number of bolts to connect the members on each side. That is, let us show the arrangement of the bolts and the members in the case of double cover butt joint. So let's see, show the plan of the joint. This is one cover plate and we have another cover plate below. So this is a top plan, and we will have the seams of the two plates, main plates, as this. So we have 250 kilonewton load on the joint, and the number of bolts is 3. So we have 3 bolts here, and we will have 3 bolts on the other side of the joint as well. Actually it is double cover butt joint, and we have the longitudinal section like this. So we have bolt line here and bolt line here. Now actually we have not incorporated this value of beta pk in the calculation of design shear strength. So we have mistaken. So we will multiply it by 0.9 here, then only we will get 81.47. That means we are applying the reduction factor for the packing plate, and the shear strength gets reduced by using the packing plate. So the bolt value will remain the same, and this will be the actually the arrangement for the bolts in the joint. This is one bolt line, and you will have another bolt line here. This is the longitudinal section of double cover butt joint. So that was all in today's lecture. Thank you.